For centuries, a really simple, powerful idea has been at the heart of science. If we can just understand the tiniest little pieces of the universe, we can understand the whole shebang. But what if that's just wrong? Today we're diving into a landmark 1972 paper by physicist P.W. Anderson that argues the science of everything doesn't actually explain anything.
I mean, this is the ultimate scientific dream, isn't it? If we could just nail down the fundamental laws that tell every little particle what to do, shouldn't we be able to work our way up from there, predicting atoms, then molecules, then cells, and eventually maybe even us, human consciousness itself?
Well, this big idea has a name. It's called reductionism. It's the belief that everything, and I mean everything, from a galaxy to a brain cell is ultimately just playing by the same set of fundamental physical rules. And this isn't some fringe theory, It's pretty much the bedrock assumption of most modern science.
And if you can break everything down into its smallest parts, it seems totally logical that you should be able to build it all back up again. This is what's known as the constructionist dream. But this is exactly where the logic completely falls apart.
And that brings us to P.W. Anderson's incredibly powerful counter-argument. And it's all captured right there in the title of his paper, More is Different. He basically argued that this leap from taking things apart to building them back up is a huge fundamental mistake. Here it is, right from the man himself. Anderson's core point is actually pretty simple. Think about it. Taking a watch apart piece by piece doesn't automatically teach you how to build one from scratch. Reduction and construction, they are not two sides of the same coin, not at all. To explain this, Anderson lays out science as a kind of hierarchy, like a ladder. At the very bottom, you've got elementary particle physics. That's the foundation for the physics of bigger systems, which in turn is the foundation for chemistry, then biology, and on up the ladder. So, of course, the things at a higher level, let's say cell biology, they absolutely have to obey the laws of the level below them, like chemistry. No one is debating that. But, and this is the absolute crucial point, that does not mean cell biology is just applied chemistry. It's not this simple one-way street of understanding. Because at each step up that ladder, when you start putting more and more particles together, entirely new behaviors just emerge. And these new behaviors, you can't just predict them from the level below. They demand new ideas, new research, and totally new laws to even begin to understand them. The whole becomes truly fundamentally different from the sum of its parts. But how does that actually happen, right? How does simply adding more of something create entirely new rules out of thin air? Well, Anderson's explanation is wrapped up in this really fascinating concept from physics, broken symmetry. To explain it, Anderson uses the ammonia molecule as the perfect example. So it's shaped like a little pyramid, right? It's got a nitrogen atom at the top and 3 hydrogen atoms at the base. This lopsided shape gives it a specific electrical property. Okay, and this is where it gets super weird. The fundamental laws of quantum mechanics that are running the show here, they are perfectly symmetrical. They don't care about up, down, left, or right. So a truly stable object following those laws shouldn't have a lopsided pyramid shape. So what's going on? Okay, here's the secret. That molecule isn't just sitting still. The nitrogen atom is constantly tunneling through the base to the other side. It's flipping itself inside out about 30 billion times a second. It's incredible. So its true state is actually a perfectly symmetrical average of both the up pyramid and the down pyramid. The pyramid shape that we see at any given instant, that's a temporary state of broken symmetry. The laws are symmetrical, but the structure we happen to observe is not. Now hold on, because this is where it gets really profound. This whole idea of broken symmetry doesn't just apply to one tiny little molecule. It scales up. And when it does, the consequences are just astonishing. Let's just scale this up. With ammonia, that flip is happening at a mind-boggling speed. But now take a bigger molecule, like a sugar molecule, with about 40 atoms. The energy it would need to flip is so immense that it basically never ever happens. The molecule gets locked into its asymmetrical shape. Okay, now imagine a crystal with trillions upon trillions of atoms. That asymmetrical state is permanent. The entire system now has fundamentally less symmetry than the physical laws governing its individual parts. Think about that for a second. And this just perfectly illustrates Anderson's point. By simply adding more parts, you don't just get a bigger version of what you started with. You get a system with entirely new properties. That ability to flip, it's gone. A new kind of rigidity, a new kind of structure just appears out of nowhere. And look,
this isn't just some abstract theory. Take something like superconductivity. Physicists had all the fundamental laws they needed to understand it for 30 years before they could actually explain it. 30 years. Why? Because superconductivity is an emergent property of a huge collection of electrons. It's a state of broken symmetry that you simply cannot predict by looking at one or two electrons on their own. So let's bring this all home. The central, mind-bending idea here is that a change in scale, in pure quantity, can lead to a fundamental, revolutionary change in quality and behavior. And here is why this matters so much. It means psychology isn't just applied biology. Biology isn't just applied chemistry. At each new level of complexity, totally new concepts emerge that require fresh, creative, fundamental research. You can't just derive them from the level below. Like Anderson said, intellectually, it's a one-way street. Anderson closes his paper with this absolutely perfect anecdote. F. Scott Fitzgerald once said to Ernest Hemingway, "The rich are different from us." And Hemingway, being Hemingway, shot back, "Yes, they have more money." Well, in this debate, Anderson is firmly on Team Fitzgerald. The quantitative difference, just having more money, creates a truly qualitative difference in their entire reality. More is different. So the crucial point to take away from all this is that complexity itself is a fundamental ingredient of our universe. It creates new rules and new realities at every single scale, which, of course, leaves us with a final question to chew on. A few lines of code become an AI, a few people become a city. Where else does a simple change in quantity create a totally new and often unpredictable quality?